Hi everyone, let's talk about cyclohexane. 6 carbons in a ring, and all 6 carbons are singly bonded, single bonds. So we're continuing the second half of Key Concepts, Unit 1, Part 5. So find that document on Canvas. It looks like this at the beginning where we talked about naming the cycloalkanes. And then what you want to do is just scroll down until you see conformational analysis of cyclohexane. So I cut that part out for this slide. Here we are. Okay, things are a bit busy on this page, so we're going to come back to it in a second. But that's where you want to be, conformational analysis cyclohexane. Oops, little typo there. Conformation. Should have been conformational. Okay, let's back up, get a little background real quick. Cyclohexane, as well as the cycloalkanes, alkanes all have 4 single bonds to carbon. The carbon is sp3 hybridized, right? And sp3 hybridization means that the carbon has tetrahedral geometry. Bond angles of 109.5 approximately, 0.5, sorry. And what does that do? Well, it means our rings are not flat. We draw them flat, right? 3 in a ring is a triangle, a square, pentagon, hexagon, heptagon, octagon. And that's a cyclopropane, cyclobutane, cyclopentane. Yeah, you get the pattern. But if you look at their 3-dimensional shape, they're not flat. Well, cyclopropane is. 3 points have to be in a plane. But beyond that, even the square shape is bent. Cyclopentane, cyclohexane, yeah, they all have irregularly, not flat structures. Furthermore, single bonds can rotate. The ring is going to limit how much they can rotate, but they still can wiggle and twist and change their shape. Okay, so yes, there's lots and lots of alkanes that form rings, but one of nature's favorites is 6 atoms in a ring. A lot of times it's 6 carbon atoms in a ring, and that's what we're going to look at today, cyclohexane. But sometimes oxygen and nitrogen get into that ring of 6 atoms too. There's a lot of biologically relevant molecules that have rings of 6 atoms. And in biology, shape is important for determining how molecules react and interact with other things. So this is a tool that'll help you in the future to analyze shapes of molecules. We're going to look at the shapes of cyclohexane. Scientists would say we're doing conformational analysis, right? Different conformations are different shapes. Okay, and this is a neat little energy diagram. You've seen that in a previous video or two. And it's showing you the energy diagram for the shapes, the conformations of cyclohexane. And down here at the bottom of the curve on the left, the bottom of the curve at the right, those are the energy minimums. These are the more stable structures of cyclohexane, the so-called chair conformation. Okay, so now you can look at the side over here. I think of a lounge chair next to a lake or the ocean, something nice, relaxing, and this person laying out on that lounge chair, which is actually, I guess it's this chair structure. So cyclohexane, viewed from the side, kind of resembles a chair when it's in its most stable shape. And yeah, I'm a visual person, so that helps me understand what I'm looking at when I look at this distorted hexagon. It's like, no, this part right here is the head of the chair, and right here is the foot of the chair, just like this person's laying out here with this nice little cool drink here. Distractions, stop that. Okay, there are other shapes, and hey, they got names. That's what scientists are good at, putting names and labels on every new idea. Okay, yes, those are cool structures and different shapes, but they're less common because they're more unstable, more reactive, if you will. They want to twist and get into the more stable chair. So in this class, we introduce the idea, but they're not going to show up on exams. The chair forms, however, the most common forms are on exams. So let's look at that in a little more detail. These pictures are nice, But moving pictures are better. Let's go look at some animations on YouTube. I think it's here. Let's find out if it is. Nope. Oh, I know where I need to go. Sorry. That's where I found that picture. Okay, come on. We need to go here. Oh, boy. Oh, this picture. And I just want to make sure you're looking at this. So one more time. Good. Had some problems screen sharing in the past. Okay, the link to this website will be found in the comments. I will also post it separately in the second place on Canvas. Let's go full screen so you can see it. What are we looking at? We are looking at the edge view of cyclohexane. The 6 black circles in the center are carbon atoms in the 6-membered ring, the hexagon, view from the side. These 2 carbons are towards us. The smaller carbons are beyond us in the distance. This is cyclohexane, so 6 carbons, 12 hydrogens. And as we analyze the shape, as we do conformational analysis, these bonds where the hydrogens are attached are the most important features. They're going to help us decide which structure, which conformation is most stable. So, new ideas get new names. Turns out these up and down bonds look like axes, like an axis. I don't know. I'll show you a globe in a second. Not a globe, but I'll show you what I mean by, think of a globe. How about that? Think of the Earth spinning on an axis. We got the North Pole up, South Pole down. As it spins, the line about which it rotates is called the axis. That's why these bonds are called axial bonds. The blue hydrogens are attached to axial bonds. They're up and down. And if you're still thinking about the globe, around the middle section is the equator of the Earth, the equator. So we're going to call these red hydrogens that stick out from the sides equatorial bonds, equatorial hydrogens even. Cool. Okay, so we froze cyclohexane in place. Let's let it wiggle. So put cyclohexane into solution. The cyclohexane molecules will collide with other cyclohexane molecules. As they collide, they'll bump, distort, twist, and bend, and change their shape. So let the movie start. So let cyclohexane start wiggling. Okay, bump it around. You might see some, there's a half chair, twisted chair, boat. And it gets back in a half chair, and then it's going to pause here at a chair conformation. So should have pointed this out at the start of the video, but here, these 3 carbons kind of form the head of the lounge chair. The middle section's the seat of the chair. And then these 3 carbons are the foot of the chair. And wait, how come the up and down bonds are not blue anymore? They're red hydrogens. That's because as the chair wiggles into a different shape, a different chair, the axial and equatorial groups change places. Blue hydrogens now are on at the sides, the equatorial bonds, and the red hydrogens are up and down. Now they are axial. Now let's let the movie go as it wiggles yet again. Red is currently axial up and down, but we're going to see that blue can get in that place next. There's the boat, twist the boat, and all that good stuff. It's wiggling around, and look, the blue ones are now up and down. The red ones are back off to the side. Textbooks will say the conversion between one chair and the other chair is called the chair flip. That's a bad name. I always think of something going 180 degrees. A molecule that's frozen in place and you just spin it 180. Sounds like a flip to me. This isn't a flip. This is a chair wiggle. the textbooks, the internet, they're going to keep saying, hey, as one chair flips into the other, so go ahead and flip. The red is up right now, but wiggle, and yeah, the chair wiggle. The chair dance, maybe we should call it that. The red used to be up and down, and now the blue is going up there, and textbook will say the chair has flipped from one structure to another. Cool. So in the comments will be the link to this website. You can play around with it, rewind it, fast forward it. Trying to understand how that chair, how the cyclohexane ring is wiggling from one shape to the other. Okay, why are we showing you this? Oh boy, here are the objectives for this video, for this part of organic chemistry. There's another handout to help you draw these structures, and that's what you need to do. We're gonna have to do the analysis of shape, conformation analysis, and to do that, you need to sketch the chair conformation. And it needs to be somewhat accurate so we can do our analysis accurately. So yeah, you're gonna get some points for good drawings. So we need some practice doing that. A tip to help us get a good drawing is realize that every bond we draw is going to be parallel to at least one other bond. So as you start to draw cyclohexane, every time you do a bond, look at what you've drawn already, find something parallel to the new line you're drawing. That'll help you get a good drawing. Okay, and after you draw one chair form, you need to take it and flip it, wiggle it. You need to wiggle it into the other shape. And why are we doing that? Why are we drawing two forms of the chair? You know, the red bonds up or the blue bonds up. We need both forms. Well, it turns out that, it's down here at the bottom, the equatorial bonds have more room. So that's where nature will put the big bulky groups. They'll put them on the edge, the equatorial bonds. And if the groups are not there, it'll try to wiggle its way to the other chair form, because as the chair flips, we saw the red bonds become blue. Yeah, axial bonds always become equatorial after a chair flip. Something to keep in mind, though, is that we'll see in a minute that if the bond was pointing upward axial, the equatorial bond still points upward a little bit. That'll be helpful in our analysis. Okay, more examples coming soon on this fact. Right now, we're just getting our objectives out of the way. You need to be able to look at your drawing and be able to say, hey, which bonds are axial, which one's equatorial? And again, if your drawing sucks, it's gonna be really hard to do that. So we need to take a few minutes and get some practice drawing chair conformations. And then after you draw and identify axial and equatorial bonds, we're gonna look at crowding. Again, the main idea, equatorial bonds are less crowded. Why? Well, because axial bonds are more crowded. And the proper scientific term is you get 1,3 diaxial interactions. Yeah, we're getting crowding at the axial groups. And based on that, we will be able to predict the more stable chair conformation, right? There's two forms of the chair. Either the red bonds were up or the blue bonds were up. One of them is going to put bigger groups equatorial. That's the more stable form. That's the form nature prefers to have the molecule get into that shape. All right, those are our objectives. Let's break them down, get some practice, and get more comfortable with this, with these objectives. Let's see if they need to go up here, go up here, maybe, no. Let's just leave those objectives here and we'll start drawing. Oh, I know where we need to go. Going back to the top of our objectives, let's start looking at drawing it. On canvas, there's another handout. Let's see if this will take us to it. Yes. Okay, so there's another handout. Some quick information about chair conformation cyclohexane. Let's just go through this real quick. There's some interesting information here. In a previous video, we talked about Newman projections. So we actually can, let me get, so these are Newman projections, two of them side by side. And yeah, use both eyes, look down both bonds. Weird. Okay, but if you look at the edge of this chair conformation, from one perspective, look at the carbon 1,2 bond, that will show up as a Newman projection. And if you look down the 5,4 bond, 5,4 bond, that's another Newman projection. And you can see that when cyclohexane is in a chair shape, chair conformation, all of the groups are staggered. And staggered is more stable than eclipsed. And if you were to wiggle cyclohexane and get into, let's say, the boat conformation, and then drew Newman projections of the boat conformation, you'll find some eclipsing groups. Eclipses are crowded. The electrons around those groups are repelling. And it turns out when the ring is in a chair conformation, you get the nice, stable, staggered conformation, right? Hydrogen, 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 hydrogen. Then you have the CH2 group separated by hydrogen. Everything's nicely spaced out, alternating and staggered. Cool. Okay, next idea on this page. If you could spin cyclohexane, it would spin about an axis, the ring axis, which is vertical. So all the vertical bonds, these red hydrogens are on vertical axial bonds, they're called. And if we think about the planet Earth, around the perimeter, or that's not right, around the edge, the fattest part of the world, if you will, where it's spinning, around the ring here, groups that are sticking out, the blue hydrogens are sitting on equatorial bonds. Here's a nice drawing. That's our goal, to draw something like this. And again, you need a good chair. The carbons need to be in the right shape so that when you attach the axial and equatorial bonds, they look like. Okay. Here the page. There we go. I like this because, this is a space filling model on the left, and a normal, what is this, ball and stick model on the right. Okay, we're more familiar with the ball and stick model just because it's easier to write in the H's here and the C's here, and it's nicely spaced out so you can clearly see the bonds. But the space filling model on the left is more accurate in terms of the actual shape of the molecule. We're focusing here on electrons. So at the top of this drawing, both drawings, is a hydrogen. So at the center of this circle is one proton in the nucleus of hydrogen, but the bonding electrons, the 1s electrons that are being shared with carbon, they're orbiting the nuclei, both the hydrogen and the carbon. They're out in space, and this is kind of showing how far out those electrons tend to roam. And then we have hydrogens over here. We got the red hydrogens pointing up. And now you ask yourself, well, where's the crowding? Well, look at this tiny little gap between the red spheres. These electrons are getting really close together. Now look at the space between the blue spheres. It's bigger. There's a larger gap. There's more distance, less steric repulsion. And so these hydrogens out at the perimeter, I keep saying perimeter, but that's what it looks like to me. These hydrogens at the equator enjoy more room, more separation from their neighbors, they're more stable. And these axial groups, they're all crowded together here. Okay, and here's the main idea. Groups that are equatorial have more room. That tends to make a more stable structure. So 3 drawings, all the same shape of cyclohexane. Here, let's start over here on the far left. Cyclohexane is a methyl group on an axial bond, pointing straight up and down. And we got these arrows saying, hey, if the methyl group is on carbon 1, there's an axial hydrogen on carbon 3, and another axial hydrogen on carbon 5. Let's just look at carbon 3 for a second. The hydrogen that's axial is overlapping with a methyl group. They're getting close together, and that's a space-filling model on the bottom suggesting. The methyl group is crowding in on those axial hydrogens, and that's making the structure less stable. The molecule would rather wiggle and put the methyl group over here equatorial. And now the methyl group sitting out the side, you can more clearly see in the bottom right, the group is farther away from other electrons around the other atoms. That's more stable. You might be saying, well, they're closer, but not touching. Isn't that okay? Remember, the electrons don't have to touch other electrons to interact. Electrons are negative, and negative charges repel. You know what? Very much like magnets repel. So think of magnets when you think about electronic repulsion. Where did I hide it? Hide it here. Yeah, I found another quick little video. Get out of full screen. There you go. Good. This one. And then I want to make sure you're seeing this. So let me load it up one more time. All right. So this person is holding two magnets, and he just twisted this magnet so the North Pole faces the North Pole. So North Pole magnet with the North Pole magnet is going to repel. So think of this as maybe an electron in one atom, one of the axial hydrogens, and this other magnet might be the electrons around the methyl group, and you don't have to touch the right? So that's a big push. Look how far away these electrons are. They are going to repel each other even though they don't touch. So that's a nice visual. Think about what the electrons are doing when they are axial. So avoid the axial interactions. The molecule can still get in this shape. If the molecule is found in this shape, this chair with the methyl group off the side, another solvent molecule, another cyclohexane molecule can collide with it and punch it, if you will, and all that kinetic energy can force it, cause it to wiggle into this unstable shape, and then it can wiggle its way back. And so it truly is an equilibrium. But the equilibrium favors the bulky group equatorial. Okay, so big idea there. Bulky groups prefer equatorial bonds. Okay, nice. Let's practice drawing the chair conformation. So there's a handout on Canvas that goes step by step. What I'm going to do is just kind of roughly follow that procedure. And let's draw cyclohexane in a chair conformation. Let's fatten up the line here so it's a little easier to see. Okay. Let's draw a chair conformation. So what you do is you start by drawing two lines parallel, right? That's the big hint. After you draw one line, every new bond that you draw has to be parallel to something else. So I'm going to work on the seat of the chair. So instead of starting here exactly at the same position, you want to skew it a little bit. There we go. Those two lines are parallel. And that is a carbon-carbon single bond, another carbon-carbon single bond, and I'm working on the seat of the chair. All right, let's draw the head of the chair, or work on the head of the chair. So this bottom one, like this perhaps, and that's okay, made a little mistake there. I'll clean it up in a second. I drew in a line, and now I want to draw another bond, another line that's parallel to that one. Ooh, I got a little nervous and shook a bit. It's okay, that's decent. And now connect the dots, close up the ring, but do so that things are parallel. So I might want to extend this a little bit more and then connect it. And then as I made that slope, I get the same slope going here. Ooh, man, that wasn't too bad. I've had a little practice, and it's not perfect. It does not have to be perfect. Nice. And if you're using a computer, Hey, cut and paste this. Nice. All right, so I'm using paint. That's available on any computer that's using Windows. It comes with Windows, Microsoft Windows. All right, let's take the chair and draw in the all-important axial and equatorial bonds. Let's start with axial first, because they're straight up and down. Okay, so where are they? Well, remember in the video there were 3 red atoms up and 3 red atoms down. So that's the first pattern, is they alternate direction. Sometimes axial bond points up, and sometimes axial bond points down. Which carbon bears the up bond and which one bears the down bond? Okay, well, as you look at this, okay, I'm gonna pick over here on the far left. I'm gonna start here. And you can start anywhere on your hexagon that's bent into a chair. Okay, but if I look at this one, you can see that the next 2 carbons are down. This carbon's like sitting on a mountain peak. So stick your flag at the top of the mountain peak. That's supposed to be straight up and down. That's better. Okay, so on the peak, your axial bonds are going to point up. But over here in the valley, right, so this carbon, the next carbon's up from it, the next other carbon on the right is also up. We're kind of in a valley. The axial bonds are going to point down, and it's okay to stop them short. The other thing you can do is go through that bond and point it down. Your choice, your drawing. Either one's acceptable to me. Now that we had, as long as you found your first mountain peak and you got up, just alternate them. So axial bond up, axial bond down. Axial bond up, it's also on a mountain peak. Axial bond down, this one's in a valley. Axial bond up, and if you want to stop short, you can. Put a little H there. And then over here, this last one, kind of blur it with the dot. Clean up my hair, my overlap. And then now we're down. There's a hydrogen. Good, we got all 6 axial bonds. If I walk away saying, I'm all done, that's all I want to draw, what's the name of this molecule? Well, if you don't draw any atoms, it's a skeletal drawing, so we assume that's a carbon or a methyl group. And we have 2 of them. And if you want to number the ring closest to your branches, the methyl branches, this would be 1 or that's 1. If this is 1, then that's 2. This molecule is 1,2-dimethyl cyclohexane. So I want to point out that after you draw your bonds, at some point later, go back and fill in the atoms. Or if you don't have any groups, if they're just hydrogens, you can just leave it empty without any axial equatorial bonds. Like right now I'm saying, hey, there's 2 H's here in a skeletal drawing. You don't have to draw in the bonds to the hydrogens. You don't have to draw in the H's either. So this is a good drawing of just cyclohexane, and for whatever reason, I decided to draw on 1 of the hydrogens. My choice, right? When you're drawing it, you decide how to draw it. Okay, I don't want 1,2-dimethyl cyclohexane. I want cyclohexane. So now I'm compelled to put H's at the end of my bonds. Otherwise, someone else might think that they're methyl. Okay. Let's copy and paste. Let's clean up. Get rid of that floating hydrogen. Go away. Ooh, you know what? Maybe I'll switch to red. All right, I'm going to start over here on the leftmost carbon. Deep breath. We can do this. Axial bonds are easy. They're up and down vertical. Equatorial bonds are a little more difficult. They are never perfectly horizontal. They are not. So do not draw it that way. You lose points. And more importantly, you can't analyze the shape correctly if you draw it like that. They are not horizontal. But think of it, that's a good idea. It doesn't go this way either. That's going to crowd out. The bond doesn't go into the chair. Getting too close to all these bonding electrons, there's a lot of repulsion. Okay, so for equatorial bonds, equatorial bonds, they point away from ring, from chair. Point, not paint. So this hydrogen, sorry, this carbon will have an equatorial bond on the left side, but this carbon will have an equatorial bond on the right side. It's going to point away from the chair. If you look at this carbon, well, I know there's still chair on the right and the left, but there's more room on the right side. The equatorial bond for this carbon is going to be on the right side, away from most of the chair. Same is true for this carbon's equatorial bond. It's going to be pointing to the left. So equatorial bonds point away from the center of the chair. Start horizontal, but move away from the axial bond. What do I mean by that? Okay, so let's go over here on the left, and we start thinking it's supposed to be going out completely level horizontal. It's not, though. It's not going to be perfectly horizontal. It's going to be moving away from this up axial bond. It has to come down. Well, how much of an angle? Well, remember the key, every new bond you draw is parallel to one other bond, at least one other bond. So as I start to think about a bond going down and to the left, I see the seat of the chair that's also down and to the left. So that's what I'm drawing parallel to. It's also going to be parallel to this one. So I don't know. That was good enough. You know what? I'm making a video, so I'm going to do better. And I still did. I like that better. And at the end of this bond, it's pretty long. Doesn't have to be that long. I'm just trying to emphasize how the slope of this line is parallel to the seat of the chair. Let's go over here to this carbon. Again, you're starting out horizontal, but it's not. It's going to move away from the downward axial bond. So you need to move up. And that's going to be parallel to this line. Let's go over here. And now we want to think about going horizontally away from the center. But go down, and yeah, I know it's going to be parallel to this line, but you don't want your bond on top of another bond. You won't be able to see it. So don't draw your axial bond on top of this one. Instead, go into your parallel to this one. Awesome. Keep going around the ring. This carbon is going to start out horizontal away from the center, move away from the axial, so you're parallel to the seat of the chair again. This carbon here, start out horizontal, but you're going to move down away from the axial bond, right? Electrons repel, bonding electrons repel. So go parallel to this line here. Right there we go. It's a decent chair. Okay, let's copy and paste that. Actually, let's do something else. Let's copy and paste this one. Because this one is messy with all those horizontal dotted lines. Okay, let's go around real quickly. I want to be away from the center, parallel to the seat of the chair. This one's going to be away from the center, parallel to this other bond over here. This one, it's going to move away from the axial, but don't go on top of this close bond. Go parallel to this other bond over here. This one starts horizontal away from the center of the chair, but go up until you're parallel to the seat. This one is going to be parallel to this bond right down here. Good. And now our head of the chair is on the left. The foot of the chair is on the right. Now what I want to do is wiggle it, do the chair flip. That's the scientific term. No, that sounds very, very scientific. You can call it chair wiggle. So it's going to wiggle its way. And so start with the C of the chair. You can see that two parallel lines pointing up and to the right gives us a chair on the left. Now we have to undo that. We have to go down. Let's make it a steeper incline. That. Messy. It's okay. Clean that up a little bit. I think these lines about the same length. Okay, and now we want down bond and another down bond that's parallel. Now we're going to close up the ring, and I'll make this one first. So look at that incline and do this one about the same. And kind of fix it. That's okay. I got the chair, got the carbons of the chair, and now I'm going to start at the highest carbon. That's this one. So this one's pretty high up on the page, but this one's higher. So I like starting there. We're up on a mountain peak. Axial bonds point up on peaks, and they point down in valleys. Up on a peak, down in a valley. Up on a peak and down in a valley. Equatorial bonds point slightly. They start out horizontal, away from the center, but they move away from the axial bond, so this one's going to point down until it's parallel with the C of the chair. Over here next, this is going to be away from the middle to the right, but up until it's parallel to this bond. That's pretty close. Over here, go away from the middle, so point left, go down, not on top of this bond, but parallel to this bond. This one over here, it's going to move to the left, wiggle it up until you're parallel to the C of the chair. Over here on the top, mountain peak gave us the axial bond, so we want equatorial bonds pointing down, parallel to this one. Last one here, it's going to be horizontally pointing away to the right, away from the middle of the chair, but move away from the down axial bond, not on top of this bond, but parallel to this one. Right here. There we go. We have the other chair flip. Yay! Okay. And then if I ask you, well, let's put a bromine atom right here. We now have one bromocyclohexane. Where's the bromine over here? Well, you gotta be consistent. What happens in a flip? Well, the axial bromine is now gonna be equatorial. Let's go take a quick peek at the video to confirm that. And I'm not sure if you're seeing the video, the chair animation. So I'm gonna go back there one more time, just make sure you get it. Okay, so that's not where our bromine was. But let's just see the pattern. Let's look at this blue hydrogen, see where it goes. Well, right now it's on the mountain peak, right? These three carbons form a mountain peak. This is the head of the chair. You look at the other three carbons. This carbon over here on the far left is pointing down with respect to the rest of the chair. This is the foot of the chair. Let's focus on the head of the chair, this highest point of the carbon, and its axial bond. So what becomes to the head of the chair with its blue axial bond? Play the video. Watching this carbon on the right, it's right here, it's wiggling, and it's still wiggling. Oh, I just moved down. Now, we're at the other chair conformation. What used to be the head, what is it now? It's down. It's the farthest down carbon. This is the foot of the chair now. What became of its blue axial hydrogen is now equatorial. When this carbon was the head, the blue hydrogen was up. And let me ask you this. The blue hydrogen, is it more up or is it more down? It's up, right? It's slightly up. So as an axial bond becomes equatorial, what was standing up is still standing up, pointing up. That's the pattern. That's what we need to know to do our conformational analysis. Okay, so this bromine here is axial. It's not on the head of the chair though. Where's the head? The head's over here. So it's on the mountain peak at this corner. Here's the foot of the chair. Down here, the bromine is on the far side, away from us. Right, so this carbon here is close to us. This carbon is away. After it flips, this is the foot. It's going to become the head. Where's the head? Oh, it's right here. Here's the head of the chair, right here. And then if we go back here, the foot of the chair is here. How far away is it from bromine? 1 carbon away. And you go from here to this one, we're going around the ring counterclockwise. So you have to say, you have to have the same orientation. If you're going from the head, which used to be the foot, you have to go counterclockwise to find out where that bromine is. Well, on the foot, we go over 1 carbon, we find the bromine. So from the head, go around to the back, the bromine is going to be attached to this carbon. On the equatorial bond, the bromine's right there. Not the axial bond, right? So the pattern is, bromine was axial up, so it has to be equatorial up. And you can't put it on this side, because that's not how the chair wiggled, right? The foot went up, this bromine went to equatorial bond, sticking still up. And it's on the far side of the ring, just like it started, far side of the ring. Cool. This video is getting kind of long. Let's just cover the last idea and we'll call it quits. I'll record another video so we can look at the analysis and an example in a little more detail. Okay. Let's go back to paint. It's just there, sorry. Last idea. There it is. Okay, the last part of key concept, unit 1, part 5, is the use of deuterium in organic chemistry. So as a quick review, there's 3 types. You can read through this on your key concepts later, or pause the video. But the main idea is that deuterium is the name of hydrogen. It's the name of hydrogen. It is hydrogen, but sometimes hydrogen comes in with 1 neutron. Most hydrogens don't have a neutron. So let's see, what's the ratio? Here we go. 99% of all the hydrogen on planet Earth is simply a proton in the middle. 1% of the hydrogen we find is deuterium. There's also a fat neutron in there. Neutrons carry no charge. They only add mass. And a neutron weighs about as much as a neutron. So deuterium is twice as heavy as most hydrogens. And if you want a name for the type of hydrogen with no neutrons, that's protium. And guess what? chemists are able to put on one type of hydrogen or another type at control, with control. So we can actually put a deuterium atom, which is hydrogen, a fat hydrogen, twice as heavy as a normal hydrogen, and we put it on molecules where we want most of the time. We have control over some of our reactions. And it turns out we have methods to detect where that heavy hydrogen is, where deuterium is. And it can be useful for analyzing molecules, maybe even conformational analysis. So you're going to start seeing the letter D show up. D is not on the periodic table. You need to remember that is hydrogen. So all the reactions, all the characteristics that we learn about hydrogen, same for deuterium, it's just twice as heavy, and it's a marker. We can follow this specific hydrogen. It's deuterium, twice as heavy. So here we go. How can we use it in conformational analysis? Well, I'll put deuterium on here as one of the hydrogens. Turns out it's equatorial. Do the ring flip, and now it's axial. And because deuterium is hydrogen, comes in with one valence electron, and the electrons where they orbit determines the size of the atom. Deuterium is just as large as hydrogen. Actually, if you take a physics class, I think quantum mechanics say that deuterium is actually slightly less. I can't remember the reason why. Maybe because mass creates a gravitational field, so this is twice as massive. But that gravity effect might be pulling the electrons closer. I think deuterium's slightly smaller. I don't even worry about that. For the most part, for the chemist, deuterium's the same size as its hydrogen. And so there's no extra bulk if deuterium is axial, or if the normal type of hydrogen, it's going to be down here, this hydrogen is going to be interacting with the hydrogen on carbon 3. We're getting a 1, 3. Let's see if we number ring 1, 2, 3. Carbons 1 and 3 have hydrogens that are colliding. Same is true over here. It's carbon 1, 2, 3. Carbons 1 and 3 have hydrogens that are colliding, 1, 3 diaxial interactions. That's happening. We get some crowding. Don't like it. Sorry, cyclohexane. You're going to get the same amount of repulsion in this chair as this chair. You also get this hydrogen interacting. Well, why do we have to go clockwise around the ring where we're numbering? This molecule is symmetrical. Yeah, you could have chosen to go 1, 2, 3 around the ring this way. And now we still have 1, 3 diaxial interactions, but it's between these two hydrogens. Deuterium is still hydrogen, just a special form. Okay, but if you put on a bigger group, like a methyl group, now equilibrium is not equal, roughly 90%. It depends on the temperature. 90% of the time, not 90% of the molecule. One molecule can flip back and forth as it wiggles. But if you take a quick screenshot of all the cyclohexane, all the 1-methyl cyclohexane molecules, you'll find about 90% of them at any one time in this shape, this conformation, where methyl is equatorial. But you still find about 10% of the time, what's that methyl doing in the more crowded position? It just has higher energy. Somehow it collided with something and forced it to wiggle so that the methyl group is now crowded. And it can't immediately flip back, because if you watch the video, as it flips from one chair to the other, it has to go through the boat and the twisted boat conformation to get there. And you get a whole bunch of eclipsing interactions. You get a whole bunch of groups that are even closer to each other. So as you go from one chair to the other, there's a lot of obstacles in the way, a lot of repulsion. So once it's in one chair, it kind of hangs out there until it gets enough energy to get through the twisted boat and the boat conformations to get to the more stable chair. Okay, that's enough for today. I'll see you in the next video.